Okay, yeah, hello everyone, welcome back to the channel. My name is Mtanda Samir. So this time around we are in for the mighty Jjeb, which some people call Ginger Joint Examinations Board, and now we are in for their physics paper and we are going to look into it in details. Okay, now in here we are going to look at item 1 of physics 2025 strictly is what we're going to look at in here. A good and also a learning point. In fact, just know as far as physics is concerned, at least I can see there is very many learning points in the items in this paper. Especially item 1 is very enticing. Okay, and if you're a learner in senior 4, please I would urge you watch this video to the end such that you don't miss out a bit of it. Okay, what will it sound like if you just say I watched the video a quarter way and maybe part of it appeared in the forthcoming exams, part of it appears in your neighbor, just like how I wish I watched it all. Anyway, this is the only time we have, nothing more, nothing less. So in our J paper we have a lot to learn. Please be there to watch to the end. Once again, my name is Mtanda Samir. All right, good. Now anyway, let's proceed. Yeah, again we simply call you to subscribe to the channel. Please, I even clarified and I said soon or later, for whoever has subscribed to this channel by, in fact, okay, in just 1 week time I'm going to limit this channel to only my subscribers. Okay, yeah, it is a disservice watching a video and you have not yet subscribed, don't you see? All right, so I'm going to have it limited to only those who have subscribed. So better subscribe as early as possible. In fact, first subscribe, because you never know, even tomorrow as you'll be searching around, you no longer be able to access this channel because you will have not subscribed. Anyway, that has been as the by the way. Let's see, proceed or go to the real work. We make some bit of analysis. Here we go. All right, good. So we are in for the J paper 2025. Let's get it started. Let's start on it slowly. In fact, we say slow but sure. So they're saying local raw materials for production of thermal energy are scarce in your desert stricken community. As part of your school project, you and your classmates have installed the device in figure 1A. Of course, the figure is like there. Is okay to be an alternative in cooking in every home in some hours during the daytime to address the problem. Yeah, of course this device I think uses only sunlight. This device uses only sunlight, and I know of course at night you'll not be having the sunlight, so you won't be able to eat, or maybe you cook lunch and supper all at once. Okay, so the community members are told that the device uses the sun and its mode of operation relies on the laws of reflection. Oh, that's good. Then we proceed. Please, I told you it is an enticing one. You better keep on here. It's an enticing one, by the way. So this new development is announced on a loudspeaker late in still night rather than daytime, for the message to be heard clearly by everyone in the community. Due to the exposure of the community to the sea, too many waves of water have resulted into endless flooding, causing fear in people. The radar system built in your area that monitors movement of the water displays the analysis graph in figure 1B. Alright, I think the graph is just right there. We have it. So still a proceeding. I say it is an interesting one, better watch to the end. So now in the question part they are telling us that, alright, good, the speed of water is 144 kilometers per hour. Of course water forms the waves, right? The radius of curvature of the reflector is 160 centimeters. Okay, part A, Roman number 1. Understand the meaning of light and radius of curvature. In fact, I think we are meant to say help. Okay. Right, great. So we continue with our stuff. Okay, so we now proceed. We continue. So they're saying that the speed of water waves is that, radius of curvature of a reflector is that. You are the only person in the community who has studied physics. Help the community to Roman number 1 part A. understand the meaning of light and radius of curvature. Understand the meaning of light and radius of curvature of a reflector. Okay. Roman number 2, understand the laws of reflection. Roman number, rather part B, Roman number 1, determine the distance of the saucepan. Determine the distance the saucepan must be placed from the reflector center for the food to boil. Shall we sing that? Understand, Roman number 2, understand with illustration how it is possible for food in B, Roman number 1, above to boil. Roman number 3, identify any other field in daily life where the reflector in figure 1a is used. Shall we sing that? Okay, next part we have, right, we have, okay, part C, find the number of water waves that reach the shore of the sea every second. Roman number 2, describe the technique used to reduce on the water flooding at the seashores. Okay, explain why. Roman number 3, why sound on the loudspeaker is clearer in the still night than in daytime. Okay, now let's go look at this in details. So we get this done slow but sure. Just not is a lot but worth it. So now say we have to understand the meaning of light and radius of curvature of a reflector. Now, by you just seeing the word, this statement here, I want us to make some clarification right here. So, by you seeing this word here, radius of curvature of the reflector, are you seeing that radius of curvature of the reflector? Then that aside, there's something I want you to see. Now, radius of curvature means that here you can talk about what we call curved mirrors. And of course the question will come, which mirror are we going to use? Is it concave or convex? Let's can see that. So is it concave or convex? Okay, the picture will tell us here. Okay, the picture will tell us. So let's go and refer and see which type of mirror are we going to use here. Which type of mirror are we going to use here? By the way, since you have known the word radius of curvature has given us a sense that it may be either a curved mirror, they may be curved mirrors. Now looking at this, I think we have that surface, and now it's more like this. You see, like that. Now we'll draw two surfaces like that. Now we have this surface, another surface here like this. Now we don't know that it's convex or concave, but look, if we have a kettle right here, it means that the sun rays are coming and they're being reflected back. Now it means that this inside part here is the reflecting surface, and this outside here is the, okay, this inside part is the reflecting surface. So it means that here we have this one as the reflecting surface. Allow me use R for reflecting, and this side here is done which is coated like that. This side here is done which is coated like that. Now, of course, if you say that the inside part is done with reflecting, so which type of mirror is that, by the way? Where we have that the inside part or the shiny surface or the reflecting surface is inside. Which type of mirror is that? Is it a convex mirror or concave mirror? You must think about that. Okay, now as you think about that, let's now proceed. Now still, let's come and clarify on this. You realize that they want us to tell them, okay, talk about this. We're meant to comment on this, like get some ink here. So we have the meaning of light. We have to define for them what light is, and also tell them what radius of curvature of the reflector is. Now, a reflector is a what? Is it a concave reflector or a convex reflector? Who knows? Which of those? Now, you find that, let's give an example. When look at this type of mirror like this, whereby the reflecting surface, allow me use R, the reflecting surface is inside, that is a concave mirror. And if you have a mirror whereby, like this, okay, coated inside, but the reflecting surface outside, this one is a convex. Now realize that this one here, since the shiny surface is inside, it now becomes a concave mirror, not a concave mirror, but a concave reflector. A concave reflector. Let's think about that. So let's go there and first of all see what light is and how to define the mirror. Now, before we go into that, we must start with this. First of all, now we must be knowing what a concave mirror is. What a concave mirror is in simple terms. Now, this is our concave mirror. Alright, good. Then, what must you know about this? In a concave mirror, you must be knowing what you call radius of a curvature. Radius of curvature. Okay, now this mirror here, you see that this whole stuff here is a sphere. Let me just use that. The lens may be crooked, but just bear with it. This is the whole sphere. Now the center of the sphere here, you all notice a sphere is a sphere, which is a shape, spherical shape. Okay, it's more like an oval, but not an oval really. Now the center of the sphere, now we can use the sphere to make a concave mirror or a convex mirror. Now look, if to make a sphere, the center of the sphere, this one here, becomes the center of curvature, and from here, the center of the sphere to the pole, we call that R, which is the radius of curvature. I think you can really see it from here. From this to this, we call that radius of curvature. However, now it means that out of the whole spherical surface, in order when they make a plane mirror, rather a convex mirror or concave, they cut it out of a sphere. A sphere is that oval-like shape you're seeing. Now they come and cut part. You see they cut part of this, but you have to bear in mind that from the cut part up to the center, that's give us the center of curvature. See, now that's the point. Center of curvature is a point. Now this R here is the radius or distance. The distance between the C and the mirror itself becomes the radius of curvature. Now we say radius of curvature is is the radius of curvature of which a reflecting surface of a spherical mirror is part. Yeah, so radius of curvature is the distance from the pole of a mirror to the center, where, okay, center of a sphere, of course. Now that's why we call them, sometimes we call them spherical mirrors. That's why we call them spherical mirrors, because they come from a sphere in their making. And you can see, if this is a sphere, we cut out this area here. We also cut off this area here. Now, what is mirror A? Mirror A is a concave mirror. What is mirror B? Mirror B is a convex mirror. Why? The reflecting surface is outside, the reflecting surface is inside. Now, a point to consider here is that for us, we are on this part, which is a concave mirror. Let's go back there and see. Remember, they asked us to define what light is. Let's go and see. So simply by writing, we shall get to know that light is a form of energy radiated outwards from the source and causes a sensation of vision. Yeah, of course, light is always from a source and moves in terms of what we call rays, like that, of which a combination of rays like this gives us what we call a beam of light. And that's how we can simply define light. It's a simple one, and not bother. So again, now you must know what is radius of curvature. I've explained that. Radius of curvature is the radius of the sphere from which the mirror or reflector, now of course here it can be a mirror or reflector, from which a mirror or reflector was cut, yeah, is the radius of the sphere. Now what is the sphere? What is that sphere here? The sphere is this. So the radius of a sphere, the radius of this, so the radius of a sphere, let's go here. The radius of a sphere so the radius of a sphere, like from here up to here, becomes this radius of curvature. So that distance from the center of a sphere, R, is what we call the radius of curvature. Or it is from here that now they get this curve here, so it becomes the radius of curvature. Okay, hope that really makes some sense. Let's go to my number 2. Let's go to my number 2 and see the way forward. Okay, let's go to my number 2 simply. Of course, now we have gotten that answered. Let's go to Roman number 2. Maybe someone may want another version, which is right there. If you would want maybe another version, however, if you're writing the exams, you may not necessarily do that. So it is the radius of a sphere from which the reflector forms part. Yeah, radius of a sphere from which the reflector forms part. Now we realize that our reflector is this. Okay, where is our reflector, by the way? Our reflector is this. Is this from A to B? This one is our reflector. Now from the reflector, the radius up the center of a sphere becomes radius of curvature. Let's have try to make it clear and clear and clear. Let's go to part B, part A, Roman number 2, which says, part A, Roman number 2 says, okay, if you now first you are the only person in the community and help them to know, to determine, understand the laws of reflection. Yeah, of course, we must understand the laws of reflection. Let's go there. And of course, you all know that we have two laws of reflection. They are strictly two. And if you're a teacher, I guess you taught this already to your learners, and let's go and step into that. So let's see. So the laws of reflection, let's get them right away. Let's get them right away. Set that. Now I say there are two laws strictly. We want to get them explained right here. There are two laws strictly. We have this one and that. There are two laws strictly here. Alright, good. Now this implies that, now let's get it right here. Now the first law says that the angle of incidence is equal to the angle of reflection. The angle of incidence is equal to the angle of reflection. The other one says the incident ray, the reflected ray, and the normal, all at the point of incidence, lie in the same plane. Now what does it mean? It means that if you have a plane mirror and the light ray is coming like this, now the angle of incidence is measured from the normal, like from the normal to the ray. And since this ray is coming in, it is the angle of incidence I must be equal to the angle of reflection R. Meaning, if you have here 20, then you as well have there 20. That's the law. They're always equal. The angle of incidence is equal to the angle of reflection. Another one says the incident ray, which is this, okay, the reflected ray, which is this, if you can see that, and the normal, which is this, all at the point of incidence, they are all at this point of incident. They are all at this point of incident, lie in the same plane. Yeah, the plane is here, our plane mirror. Anyway, I think that makes some bit of sense. Part Roman number 2 done. Let's go and look at Roman number 3. I told you it is a well spiced up item, by the way, which you must watch to the end to be on the safe or right side. Now let's go and look at Roman number part B. In fact, let's go into that. So part B, they're saying, get some here. Part B, they're saying, part B, Roman number 1, you must select them to determine the distance the saucepan must be placed from the reflector. Determine the distance the saucepan must be placed from the reflector center for food to boil. Now I want to see how this food of ours will go about boiling. How will it boil? We want to know the distance. We want to know the distance in simple terms. So let's go and get that covered. How shall we know the distance? But you all know that. I will give you this. Now, the distance where this should be placed is that for any plane mirror or a concave mirror we have talked about. If this is our concave mirror, maybe I'll do it like this. Allow me to do it like this. So if this is our concave mirror, I'll use this to explain. So if this is our concave mirror like this, okay. Now what does it mean? Here we have our F and we have our center of curvature C. Now this F here is the point where if the rays are coming from the sun or the far ends and the rays are incident onto the mirror, they converge at a common point, say F, which we call the principal focus. That is the point where they will converge. And now in this picture, where you see the kettle, here like this, where you see the kettle here in this picture, where you see this kettle here is where is the distance, is the focal length, or is where our F is. Like where you see this kettle, from here up to where the kettle is, that is our focal length, say F, like that. So now we need to know that F, but how shall we get it? Let's go there. So we need to know that F, but again remember they've given us the radius of curvature, meaning the radius of curvature, say R, has been given to us here. Radius of curvature of the reflector is 160. So radius of curvature is 160 what? Centimeters. Meaning that, allow me use the different ink, meaning that as far as our mirror is concerned, the distance from here up to here is 160. But our aim is to get the distance from here up to here. That's the best position to place a saucepan such that the food can boil very well, and that is F. But we know that from R, if you like light, if you cover the light, R is equal to F. Okay, but our R is what? Our R is 160 equals to 2F. We want F, so divide by 2. We again divide by 2. You realize that your F will be simply 80 centimeters. So we find that the correct distance where we must put the saucepan in order for the food to boil very well must be 80 centimeters. With that clarification, let's go and see how that can be calculated. So we start with the saucepan must be placed at the principal focus. You all know that. I've clarified on that. The saucepan must be placed at the principal focus. Now we also remind you that from r is equal to 2f, we have that, but r is equal to 160 centimeters radius of curvature. So we substitute in the formula, so 160 will be given to f as 2f. So dividing both sides by 2, okay, that will give us our f as 80 centimeters. So we can conclusively say that, all right, therefore the saucepan should be placed 80 centimeters from the reflecting surface of the reflector, right, for the rays to converge effectively at the focal point, okay, where heat is most intense due to energy concentration. So that's the kind of reasoning we can try to bring in right here. So it can be placed at 80 centimeters. Okay, very good. Now with that, let's, I think, proceed. Let's go look at part B Roman number 2. Part B Roman number 2, let's go there. Part B Roman number 2, let's go there. So allow me erase this off. Now still here we are on part B Roman number 2. Here we are. So they're saying, help them to understand with illustration how it is possible for the food in B Roman number 1 above to boil. Like if they want an illustration, then you must of course give us a ray diagram to show how that is possible anyway. And how does the boiling come about? After the rays converge in a common point, as simple as that. So let's go and look into that very fast. But before, let's go here. We go pictorial a little bit. And we get this answered. Okay, good. Let's go pictorial now. What we have been talking about as a concave reflector in real life appears like this. The other picture wasn't all that clear. This is how it appears. Are you seeing that we have our kettle right here? Now when the light rays come, and the incident on this surface, light rays from all angles, the incident on this surface, like this, they will converge at that point there. The light rays come up there, at this point, they will converge at that point. And the very many rays, guess what? Come like that, converge there. Come like that, converge there. Very many rays come, converge there. Come, converge there. Now this point here will be too hot, will become too hot as a result of the reflector. Will become too hot, and therefore this kettle will become hot, and the food will therefore do what? Boil. Now what you must know also is that what you call the principal focus or the focal length is the distance from beneath, underneath this side up to the kettle. That one is there is the distance, say for example what? F. And the principal focus is where all rays converge after reflection from the mirror. Of course, this is the kind of mirror we have the cut right there. You can try out this project here, even right at home. Now, what you're seeing as that silvery part there is an aluminium foil. This is what we call aluminium foil. Hope you can make a local one, so long as you have reflectors. Anyway, so with that, let's go and look into this work of ours. Like, we must give an illustration. And with this, we shall begin by drawing our concave mirror. I clarified the other alone that this is a concave mirror. And then with that, we are going to begin with our principal axis. We're going to begin with, okay, that's our concave mirror. It has the outside surface which is coated like that. Okay, now let's proceed still here. All right, good. So we have that. Now we have our mirror just like that. Now it implies that here, maybe just try to figure out on some of the things here. We have that as our F right there, and have that as our center of curvature. Now this is our center of curvature. You realize that if light rays come from very far and they are incident on the mirror, in this format, light rays come from very far and they are incident on the mirror. These light rays come and they are incident on the mirror, and another ray comes and is incident on the mirror. Now where they are coming from, just know that maybe they are coming from the sun. Now when these rays come in that direction here, like this direction, every light ray will come and converge at F. Even this one also will come and converge at F. Even this one will come and converge at F. And even this will come and converge at F, if you can really look at that. So this part here is that which becomes very what? Very hot in simple terms. Let's get there. Okay, next we have that ray which will be incident at that point in that direction, and another ray comes right away from there towards the principal focus F in that direction. So we again have another ray from the other side, a ray which is parallel and close to the principal axis in that direction will also appear to go at F right there, in that direction. The arrows highly called for. Now from there, still again we have other rays up the other side, incident of the mirror in that direction, and also reflected to pass through the principal focus F in that direction. Again, another ray down this side, parallel and very close to the principal axis in that direction, will appear or will pass through the principal focus F. Now, I think that the very main line is intersecting somewhere, and then there it means that intense heat will be produced in that area. I think let's get this named like in that order. So let's get this named. That point there you're seeing is what we call a principal focus. Okay, so please, me, I prefer to use those arrows, but it's not good to use those arrows with the heads, arrowheads. I just chose to use that for decoration, but not if you're a student, you just draw a line to show that effect. Okay, so again, that is now what you call a principal axis in simple terms. Okay, so let's proceed. This is our principal axis. Take note of the SP, the principal axis. This is the principal focus. Okay, we have that as, now the rays right there are coming from, so it's a parallel beam from the sun. These rays here you're seeing, this one, this, a combination of that, they are parallel beam from the sun, like that. Okay, now we want to see how does that come about and how does the heating come about. Let's have this in writing. So we're going to say that. Okay, so you find that here, parallel beam from the sun are treated as the rays from the sun. The other ones we have here, which are incident onto there. So you say the rays from the sun are treated as parallel beam of light, since the sun is seen as a source of light at infinity. Okay, all right. So the rays, those rays, you are taking an assumption that those rays are coming from the sun, just like you have summarized here. So as the parallel beam strike the reflector of a narrow aperture. Now narrow aperture means that if you can look at that and this, they're all coated like this. Now this one has a wide aperture. Aperture is the distance from here up to here where that line is, and this. So this one has a narrow aperture. So this one also must be of a narrow aperture. And now does it mean a narrow aperture to enable that any ray which is incident there can be reflected back towards the principal focus, which is F in simple terms. Okay, as the rays are considered to be, all the rays are considered to be paraxial rays, and so they converge to the principal focus of the reflector with a high intensity. Yeah, they all converge here like this. Now paraxial rays are the rays which are near the principal axis. Like these are paraxial rays, they are considered to be near. Paraxial means very close to the principal axis. Now you realize that here they will be reflected towards this, and if I see that they are all concentrated here, and which will generate okay, creating a large amount of heat energy enough to boil. So our saucepan can be placed right in this area. What you saw in the other picture, let me go for this first of all. What you saw in the other picture is the saucepan must be, or kettle must be placed in this area here like this. The kettle must be placed in this area so that it can now be heat. In fact, not just up, but right in this area here like this, such that the rays which are reflected can meet or find it just right there. So of course we have to explain our diagram and show how the concave reflector simply works. That's our part B, Roman number 2, as simple as that. So let's go and look into part B, Roman number 3. Is it there anyway? Let's go there. So part B, Roman number 3, let's go there. Alright, so part B, Roman number 3, let's go there. So they're saying part B, Roman number 3, you can look at this. Okay, part B, Roman number 3, here we go. There is. Alright, so part B, Roman number 3, here we are. They are saying identify any other field in daily life where the reflector in figure 1 above is used. Remember, this reflector here is just simply a concave mirror. So here they are like asking you which are the other ways or real life applications of a concave mirror. Let's go right there and see those applications straight away. Okay, without wasting time, let's go there. So we have that. So other fields in daily life, where the reflector, or what you are calling the concave reflector, is used, yeah, one, it is used as a shaving mirror. Yeah, very simple. So the mirrors they use, it can be used as a shaving mirror or makeup mirror in homes and salons. It is used as a reflector of light in torches, car headlamps, and in such lights to produce parallel, all right, beam of light. Okay, so what you see in the torches, in fact, that thing which is like this, I don't know whether I ever keen about it, ever been keen about it. The stuff which is like this, it is a bit shiny inside. It's an example of that what you call a concave mirror. The next, it is used as a reflector of light in a reflecting telescope for viewing distant objects. Please, I recommend that you go and watch item 19. Item 19 has a good version of this, because item 19, in fact item 019 in our revision series was talking about a convex mirror, and here we're talking about a concave mirror. So it's good you watch the two of them such that you can get something to learn. In fact, at the end of this video, I'm going to put for you item 18 such that item 19 such that you also have it watched. All right, good. So we proceed. Okay, now to go pictorial, this is how better we can get the applications explained right here. So you realize that they are used by dentists right here. Then also they are used in, okay, of course, to give a parallel beam of light. We have talked about that in such lights like that. And you can see here we have our concave mirror. Okay, I hope that is really making some bit of sense. Let's go to part C. 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 All right, good. So part C. All right, good. The part C, what are they saying? Part C, what are they saying? All right, here we are, part C Roman number 1, there we are, part C Roman number 1, there we are. So they're saying, find the number of water waves that reach the shore, find the number of water waves that reach the shore of the sea every second. Now the number of water waves, look, the number of water waves, the water waves they're talking about are these. Look at this, these are the water waves, like that. Now the number of water waves here, the number of water waves, they're more like the number of cycles right here. Now the number of water waves will become from, so for example, to get the number of water waves in every second, number of water waves in every second, if you look at your definition of frequency, frequency is equal to the number of cycles, okay, per second. Do you see that? The number per second. I think that the number per second. So if they say number of water waves per second, here in simple terms they want a what? A frequency. But frequency is equal to what? We know that from velocity is equal to lambda f, where this one is the wavelength, this one is the frequency, and this one here is the velocity. Now in the question, do you have the velocity? Let's go and see in the question right there and see what we have. So we realize that from the question they told us that the velocity, in fact from here, if you can look at this, realize that they told us that okay, they told us that the speed of water wave is this, so meaning the velocity is equal to 144 kilometers per hour. Kilometers per hour, that's the velocity. But if you have velocity which is equal to 144 kilometers per hour, 144 kilometers per hour, you have to convert it to what we call meters per second. And how best can we do that? We say velocity is equal to convert in meters per second, you just say 144 times 1000, this is the simplest trick, over 3600. That's the best way you can convert from kilometer per hour to meters per second. So the answer you have there will be in meters per second. Why? Speed of velocity must always be in meters per second, and here you'll end up getting 40 meters per second. That's the answer we are having right there. Then what do we need from the formula of V is equal to lambda f? We need the lambda, which is the wavelength. Have the velocity right there, we need the wavelength. Now let's go there. So to find the wavelength, here, what you're going to do is, in simple terms, to find the wavelength using the picture we have right here. Okay, now how shall we find the wavelength? Wavelength, in fact, when you have, say for example, this from like this. If you have maybe this is our wave like that, back there, like that, and back there. The wavelength means this. The wavelength is just the distance from here. The distance from, say for example here, this is the wavelength, in fact, up, back, down, and there. So the wavelength is the distance from here up to there. That's the wavelength we want. Now let's come back into this. So the wavelength will be from here up to here. This is our wavelength. And which value do you have? So the distance from here up to here will be our wavelength. Why? We have this a complete cycle from here down, back, up, and right there. So two cycles give us a wavelength. This is one cycle, this is a second cycle. So, and it is 3 centimeters. So our wavelength is simply 3 centimeters. Let's go there. So you realize that our wavelength is 3 centimeters. So our wavelength, which is lambda, is equal to 3 centimeters. But we must convert that one into what? Meters. We simply divide by 100. So this will be a 3 over 100. That answer will be in meters. And therefore your lambda will give you a 0.03 meters. Now, how shall we find the frequency? Velocity is equal to lambda f. Okay. But you all know that the velocity of the water wave was 40 after converting. We have it right here. Is equal to 0.03 times f. The f will be the number of cycles made, the number of water waves made per second. Let's go and see that in details. 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 Okay, here we are. Now, okay, this is meant to be our serial number 1. I think there was some misnumbering right here. It's meant to be serial number 1. Alright, so we are in for our part C, Roman number 1. So we had this already. Okay, so we had this already. That the speed of water wave, comma, v is equal to 144 kilometers per hour. Right there. And now we have to convert that into meters per second. Please just know we have our h right here. We have our h right there. Okay. Now we continue. So, but the velocity is equal to that. We are converting to meters per second because it was in kilometers per hour, and that is simply that I said to convert from kilometers per hour to meters per second. You simply multiply by this ratio you're seeing here, 1000 over 3600, and have it as that. So next, our lambda was 3 centimeters. We saw that, and that must be converted to meters. So you realize that we shall get our lambda will be that, and giving us 0.03 meters. So from v is equal to lambda f, let's get the line drawn there. From v is equal to lambda f, we substitute. So we shall now have our 40 equals to 0.03 times f, dividing both sides, multiplying both sides by that, and remove. Okay, this times f will give us this, half equal to 40. So divide to be 0.40 or divide by 0.03. Therefore we shall get our f as 1000. In fact, let's get this first of all. So originally we had this. Now our f is equal to 1333.33 hertz. Now that is approximately equal to 1333 hertz. Now these are the number of water waves which can be formed per second, which is the same as a frequency as far as definition is concerned. So therefore there are approximately 1333 waves per second that reach the shore. Okay, that reach the shore, and it's a repetition to say per second. As simple as that. And I hope we are simply learning something right here. That part C Roman number 2. Let's go and look at part C Roman number 3. Let's go there. Part C Roman number 3. Part C Roman number 3. Let's go right there. Okay. Here we are. And right here we go. Okay. Part C Roman number 3. Okay, here Roman number 2. Sorry. So Roman number 2 says, describe the technique used to reduce on water flooding at the seashores. Yeah, which measure do we use to control water flooding at the seashore? Okay, at once let's go there. Now let's also look at this. We are going to, in part 7 number 3, we are going to explain why sound or loudspeaker is clearer at night and than day. Meaning that why does sound travel faster at night and not the same, doesn't move slowly during the day? That's what we shall be having as our item 3 right there. So let's go and have that answered. Okay, so there, let's get there, please. Worry not, we're about to wind up with this very fast. So let's go there. So we get this covered right here. So now, what we call the barriers of floods on a sea. In fact, here they use what we call a concrete wall. A concrete wall. Let's use this. Now they're saying the technique is used to reduce on the water flooding. The technique used to reduce on water flooding at the seashores. They use a strong concrete wall built in the sea near the harbor. Now I think this is our harbor. Harbor is okay. Maybe if people are going to board a ship, okay, the area away from the land where the ship dock. I will not use the word parking, but dock, where the ship are docked, is the parking yard for the ship in the layman's language. Anyway, is what we call a harbor. So strong concrete walls are built in the sea near the harbor. You can see these walls right here. So when the strong waves rush towards the harbor, the walls reflect the sum of the waves. Now when some waves come like this, these walls will push them back like that to reduce on their speed or magnitude, and it diffract some of the few waves through the opening in the walls. Diffract means they allow some water to pass through, because we come with high pressure. They allow some water to pass through these holes here, to at least, of course, just not this continues up down the other side. So I only wanted to show you the holes here. So some water will be allowed to enter here to reduce on the pressure. So some water enter and some water is reflected back. So that will reduce on the magnitude of the wave. Okay. These protect the structures from damage by strong waves, and of course we have that covered. Now the last part was asking, why does sound travel at night? Why was the loudspeaker working better at night than during day? Simply, let's use this picture and we call it off with this. Okay, now you realize that as far as these pictures are concerned, we're going to look at two scenarios, night and during day. But what you must bear in mind is that hot air, is light. Hot air is light, and also bear in mind that wet air is heavy. Let's use that, heavy. Now what should we know is that during the day, we look at during the day, the ground is very warm during the day. Is it okay? During the day, okay, this here it is very warm, meanwhile the sky is very what? Cool, like that. Now we have your sound waves. As someone, assuming this boy is not having a loudspeaker, now as someone is talking, you realize that these waves, in fact the voice tends to move into the cooler area. That's where the voice goes. And now during the day you find that the ground is warm, therefore the ground is hot, and up in the atmosphere is very cool, so the sound moves towards the cooler areas. Therefore if you are speaking during the day, your sound will tend to go up in the air, in the cooler regions, which will make a person who will be in this area not hear very well. Now it is on the contrary when it comes to night time. When in night time, the surface here is very cool and the air is very warm at night. You have to bear with that truth. So if you are speaking, the sound from the speaker moves towards the cooler region. So if this is the boundary, this is hot, this is cool. So if someone is speaking at night, the sound will come and will be attracted back to the cooler regions on the ground, and therefore someone on the ground will easily hear that. That explains why at night sound seems to be louder than during day. Okay, regardless of whether the sound is on the same frequency. Let's get this done. We have it in writing. So now you look at that, you realize that by looking at this keenly, you realize that we're going to say the sound was louder at night because at night the temperature are low, since air near the ground is cooler than that above. Yeah, the picture has explained this. Sound travels faster in warm air than in cool air. Okay, so this leads to sound being refracted towards the ground, which makes it seem louder than during the day. So sound in cool air moves slowly, meanwhile in hot air moves very fast. Okay, so now during the day, the layers of the air close to the ground are warmer than those above it, so the sound is therefore refracted away from the ground, making it faint. Okay, I hope that really makes some bit of sense. Okay, it has been a nice lesson, and I would request that we end there as simple as that. I can simply write this for you. Maybe just say, okay, these words are for you. Okay, all right, good. Wish you well, have enough time. Please make sure you share the video to whoever may find it important. It has been a long one indeed. All right.